Hi guys, welcome to the next lecture. Moving further in limits, in our discussion today, we will be working upon the infinite limits. What do we mean by it? Essentially, the concept related to the scenario where your function is turning either bigger or bigger, or it is turning smaller and smaller. So this happens sometimes, one-sided or two-sided limits. They fail to exist. Okay. And that's happening because the values that the function is taking up, the values of the function, it is increasing or decreasing without any bound. Let's understand it using examples here. So for example, fx is equal to 1 upon x. Now, fx equals to 1 upon x, graphically, let's understand it geometrically. Graphically, it will look like this. So this graph, as you can see, it's the graph of y equals to fx, which is essentially equal to 1 upon x. So you have a rectangular hyperbola sort of situation. What is happening here? If we may look into the values, let's give values to x and find out 1 upon x. So if x is equal to minus 1, 1 upon x is also equal to minus 1. If x is equal to minus 0.1, 1 upon x will become minus 10. If x is equal to minus 0.01, 1 upon x will become minus 100. If x is minus 0.001, then your value of 1 upon x is minus 1000. At 0, the value 1 upon 0 is not defined. So I'm not going to write there anything, any number. 0.001, if x takes 0.001, clearly 1 upon 0.001 is 1000. When x is 0.01, 1 upon x is 100. When x is 0.1, 1 upon x is 10. When x is equal to 1, what do you get? You get 1 by x is also 1. So can you see what's happening here? When you are looking at values of x very close to 0, if it's a negative number, if the value of x is negative and around 0, you're getting a very small negative number. In case the value is positive around 0 of x, you're getting a very big number. If I would have continued this process, we would be getting a number which is unbounded. When it comes to the negative side of 0, that is very close to minus something. So from the negative, if you would see, what will happen? Y will be going to, or fx will be going to minus infinity. It will keep on going to minus infinity. So it's going down and down and down. It's getting smaller and smaller in terms of negative. So it's getting smaller and smaller. And that is what is going towards minus infinity. Minus infinity is perhaps the smallest, right? We don't know exactly what number it is, but in an unbounded manner, it is decreasing, decreasing, decreasing. And on the other hand, if we may see from the right, so from the right side, that is, see, this is x equals to 0, this is x equals to 0. So very close to x from the left means there will be a negative number here. And very close to x from the positive means here, it will be a positive number. So from right hand side here. Now, if you will keep on putting some x, as you can see with 0.001, you were getting 1000. You increase another decimal, then you will have 10,000 and so on and so forth. So can you see that the numbers are increasing? 1 by x is increasing, increasing, increasing. So the crux of the story here is, as x values are closer to 0, taken from the right, 1 by x will be positive and it is increasing without any bound. When x values are closer to 0 taken from the left, 1 by x is negative, and it decreases without any bound, right? So that's what you got to see from this analysis. Now let us give us some expression to these kind of scenarios. So the expression that we can give is limit as x tends to, say, a minus, that is from the left of a, fx is equal to, say, plus infinity. And when we are taking it from a plus, limit x tends to a plus from the right, fx is equal to plus infinity. What does this denote? It denotes that fx increases without any bound as x approaches a from the left as well as from the right, respectively. Okay, the two expressions. In here, we can even write down that limit as x tends to a, fx is equal to plus infinity, because what's happening is for a minus also this is happening, for a plus this is happening, whether it's left or right it's happening, so hence we can actually write it down. Now mind you, this doesn't mean that the limit exists. Limit, in case it exists, it has to be unique, right? But also it has to be a finite number. This is infinity we are talking about, but the expressions could be written like this. Similarly, there could be a scenario where limit x tends to a minus gives you minus infinity as fx goes to minus infinity, and limit as ax tends to a plus, fx is also minus infinity. So what would that denote? This tells you that fx decreases without any bound as x approaches a from the left as well as from the right, respectively, of course. And again, here also we can give it a common notation or expression, that is that limit as x goes to a fx is equal to minus infinity. I'm going to give you, geometrically, I'm going to give you an example out here. So when we are talking about a, suppose a is here. A is a positive number. You can take it on the other side also. It's absolutely up to you. I'm just taking a couple of examples. So let me just take this example first. Suppose your x is here. Now, if you are looking from the left and from the right of a, what's happening? From the left of a, you can see that the graph is going towards minus infinity. It's going parallel to this line, which is telling you that x is equal to a. And when you see the function from the right, you are seeing that it is going to plus infinity. The function is going to plus infinity. So what kind of a function is this? In case, what is happening is that it is turning into a plus infinity and minus infinity. When x is approaching a, that means this function would be looking like 1 upon x minus a. And that's why when x is tending towards a, you will be getting plus minus infinities on the either side of a. Okay, just like the case you had for x, 1 upon x, where this a was 0. Now, this time I'm taking a different number, say a. You can take x minus 1, x minus 2. In fact, practice it like that. Now, with this, I want you to pause here and guess what kind of a graph is this? What functional notation should this graph have? This time, what is happening is whether I look from the left or I look from the right of a, under both the scenarios, you can see that y is just increasing and going to plus infinity. You're not reaching minus infinity. It's not decreasing. It's just increasing unboundedly. So that means there must be a scenario where you have an even power of x minus a. Because when you will have an even power, you will not approach minus infinity. This expression will approach only plus infinity, whether it is from the left or from the right. So hence, this is a graph of 1 upon x minus a square. You can take it as square. Similarly, let's also look at these two scenarios. Now, look at this graph very, very carefully. This again is a point A. So when we are approaching from the left of A, that is a little lesser than A, x is approaching, x is on the left of A and approaching A. What you are getting is plus infinity. What you're getting is plus infinity. Why is that happening? On the left of A, your denominator, x minus A, in case that's negative, then also you're getting plus infinity, because that means in the expression you will have minus. So minus, this is a graph of minus 1 upon x minus a. And that's why the graph looks like this. You see the directions of the graph have changed. The directions have changed. So just look at that. And when x tends to a from the right, from positive, these are positive x's from the right of a, you are getting minus infinity. Why is that happening? X minus a is a positive entry here, but it's approaching 0 only. And you are able to generating it's x minus a is actually positive here. And it's moving to 0, hence 1 upon x minus a is moving to infinity. But you are getting minus infinity here, as you can see. Why are you getting minus infinity? Because there has to be minus in the expression. So that is why this is a graph of fx equals to minus of x upon a. Now look at this graph. In this graph, whether it is from the left or from the right, both approaching minus infinity. How is that happening? That's happening because this is the graph of minus 1 upon x minus a square. So x minus a square will always give you plus infinity. 1 upon x minus a square will always give you plus infinity. And since you will have a minus sign outside, that will become minus infinity. That is why in both the cases, the graph is going to, in this case, from both the directions, the graph is going to minus infinity only. So just graphically, you can really figure out what the expression would be. Either try to figure it out from the expression what kind of graph you will get, or if you just have a graph, you can actually figure out what kind of a function it would be in terms of the notation. Now that you're comfortable with graphs of this sort, I will be able to introduce to you something called asymptotes. So vertical asymptote is something which is associated to infinite limits. That is, your fx is turning bigger and bigger or smaller and smaller. Let me consider few situations here, and let's interpret that geometrically and understand what vertical asymptotes are all about. Suppose you have these graphs with you. Look at this one. What's happening here? If you see, the graph is moving and then around A from the left of A. From the left of A, if you can see, it's turning, it's going almost parallel to the y-axis. That means it is just moving towards infinity. It's getting bigger and bigger, right? So that means I can say that limit x tends to A minus fx. No matter what fx is. We're not trying to figure out the expression here. We're just trying to figure out what is the limit. I can clearly see that the limit is plus infinity, right? And on the other hand, if you see this graph, here we are on the right of, we can see that from the right of A, if we are looking, you have the function going up and up and up and up. That is, it's moving towards infinity, plus infinity. That means the limit as x tends to plus infinity of fx is, as x tends to, a plus, not plus infinity. The limit is plus infinity. X is tending towards a plus. X is coming from, we're looking at a from the right of a, okay? So that's what is happening here. If you look at this graph and look at the limit, from the left, if you will see, x is approaching a, what's happening? Fx is turning smaller and smaller. It's going to minus infinity clearly. And when you see this graph from the right, x is approaching a from the right, but fx is turning smaller and smaller. It's going to minus infinity. Okay, so these four graphs are giving you that scenario. Now, what is this scenario called? So, this scenario in which what is happening in each of these graphs, y equals to fx is either, it's rising or falling without any bound. And it's getting closer and closer to the vertical line x equal to a, but never intersecting it, never touching it, never ever intersecting it. It's just moving parallelly to x equal to a, as you can see, as you can visualize here, right? What's happening? These are graphs are moving parallelly, never intersecting. This line that you can see here, which is x equal to a, this is called vertical asymptote because this is never intersecting. So this is a vertical asymptote of the curve y equals to fx. Actually, it's coming from asymptote. Asymptotos, that's a Greek word and which stands for no intersection. And that's what asymptote is all about. So when do we use the word asymptote? When something is going parallel to some line, never intersecting it. So more so, we will be using it in a scenario of limit as if it is going parallel, that means it might be minus infinity or plus infinity. So vertical asymptote is happening when x is finite, x is equal to a, x is finite, but functional value will become infinite. And that is why you will have a vertical, the graph vertically goes parallel to this line. Whether it is minus infinity or plus infinity, it is going vertical, right? So that's how you get that word vertical here. This concept you will find very useful specifically when you have rational functions. For example, you have a function 3x square minus 6x upon x minus 2 whole square. The first thing that you would do here is you will cancel all the factors possible. So as I can see here, 3 can come out common, x can come out common, and then you get x minus 2. Whole thing upon x minus 2 square. So which will give me 3x upon x minus 2. Any which ways, guys, while analyzing this, you must understand that the domain for this function is in any which ways r minus 2. 2 was a bad number for the domain, right? And what we figure out that when we simplify this function, then also I'm getting x minus 2 in the denominator. And because of which I can, without any maths, without using any algebra out here, I can think, that around 2, it must be reaching infinities, right? So let's see what's happening here. Let us look at the limits from the left and right of 2. So say x tends to 2 minus, you have the expression 3x upon x minus 2. And from the right, you will have the expression x tends to 2 plus 3x upon x minus 2. Clearly, when x is a little lesser than 2, but almost approaching 2, it's a positive number. So in your numerator, you will still have positive. In the denominator, you will have a little lesser than 0 because it's like 1.99 minus 2. So you will get almost 0 is there, but it's negative. So that means this is going to minus infinity. With the same logic, your numerator 3x, 2 plus means little more than 2. So like 2.0001, so little more than 2. So you have positive in your numerator. In your denominator, you have something almost 0 but positive. So that means this is tending towards plus infinity. So from the right of, on the right of 2, graphically, it is that you'll have vertically going up, 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 because the value around 2 is tending towards plus infinity. And on the left, you will have vertically going down, 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 because the value around 2 is tending towards minus infinity. I've not created the entire graph. Of course, for that, you can probably see what's happening. Around 3, the value that you will get is f of 3 is 9 upon 1. That is, you'll be getting 9. So the graph goes up there. So how it goes, you'll have to see that movement. But I'm only here interested in telling you how this vertical line comes up and how this becomes vertical. We call it vertical asymptote. Vertical because you will have these vertical lines. So clearly, without anything, without any algebra, without any diagram, also you will be able to actually tell that at x equal to 2, you have vertical asymptote. In fact, have expression 3x in the numerator. So at 0, the function will give you the value 0. So it's going to cut, the graph will cut at 0 here and then move down, down, down here. And as we've already seen that from the right, it's going to be plus infinity and then falling down at 3, the value 9, and so on and so forth. So that's the kind of scenario. And what we are talking about here is vertical asymptotes. That means you have a line which is x equal to something. If here in this example, it is x equal to 2 is that line where around which what's happening is that function is moving towards plus infinity or minus infinity. In fact, in this example, it's moving to both. Thank you very much.